Hello, calculus friends. Today we're going to talk a little bit about how to deal with some problematic differential equations, or rather, how to do what are called solving first order differential equations, which are slightly different from the separable ones. I really want to make a Star Wars joke at this point, but I might save that for later. The first thing I want you to note about the equation you have first here in the notes is that it is not separable. I can't collect all the y's to one side and all the x's to the other because this dy dx is attached to this x, and that's very problematic. This is definitely not separable. That looks like I wrote Nito. Oh no. This is not separable, so you might ask yourself, oh my, what am I going to do if that's the case? Well, we're going to use a strategy today called integrating factors, and it's a little strange. So the first thing I'm going to do is I'm going to just adjust this a little bit because I really want to get the dy as by itself as I can and move as much of the y junk over as I can. So I'm going to solve for dy dx and move over any terms with y. So move over y stuff. And these are part of the steps to this strategy, and you'll see how this works. It's a little strange. Let's get this party started in mathy kind of terms. Anyway, so I'm going to start this by just dividing everybody by x to get dy dx by itself. So here I'm going to get dy dx by itself just as I wanted, equals to 10x minus 3yx. And so I'm just going to add this term over so that I end up with dy dx plus 3y over x equals 10x. Now, this might seem like some random garbage, but what I'm about to do is something insane. Yep. I'm going to take all of this and multiply it by x cubed. And that's the magic part. You might ask yourself, why the heck is she going to do x cubed? And the answer is the product rule. Let me show you what I'm working with here. So on this side, I'm going to get x cubed, the derivative of y with respect to x, plus, and I'm going to write come on, words. Over here, I'm going to lose 1 power of x, so I'll end up with a 3x squared y equals to 10x to the fourth. I don't even care what this side is because it doesn't matter with what we're about to do. Now, we're going to make a little note here. Like, this is like my side eye stuff. When you do the derivative of two functions being multiplied by each other, and I'm using this big D notation on purpose because we're going to use it a lot later, u, v, so say I've got two functions u and v, how do you do the product rule? Well, I leave u alone and do the derivative of v with respect to x, and add to it, well, now I'll leave v alone, and wait, I want to have this in order. And now I'm going to leave v alone and do the derivative of u with respect to x. I want you to take a look at this and compare it to the terms we have over here. Oh, look, there's x cubed and its derivative with respect to x. There's y and its derivative with respect to x. These are really the same thing. This is the derivative of the product of, I shouldn't have had a comma here. Shit. Because it's a product rule. I need a product here. That was supposed to be a times sign. It came out looking like a comma. X cubed times y. Do you see it? Derivative of x cubed times y. Now that I have that, hopefully you remember, when I integrate a derivative, I just get the original back. So I'm going to integrate both sides. But here we're going to be careful. I'm integrating with respect to x because I'm deriving with respect to x. I need these two to undo each other, and that's where this differs from separation of variables. Oh yeah. So on this side, I'm going to integrate a derivative, which I'm just going to get itself back. On this side, we'll add 1 to the power, 2, and then when we divide by 10 by 5, we'll get a 2 plus a c. So then if you solve for y, you get 2x to the fifth plus c over x cubed. Is that what you were expecting? Maybe, maybe not. And if you want, you could write this as like 2x, oh no, wait, yeah, x squared plus c over x cubed. I don't really care. They're the same thing. Trippy, right? This is the new method we're going to try. It's called using an integrating factor. Why do we call it a factor? Because it's used to make it so you can undo the product rule. This is a little bit messy. Let's get this party started in describing what we just did. Yes, it seems crazy, but it's the same steps every time. I want to solve for dy, move y stuff over, come up with what I want to multiply by, my factor, and then use the product rule to undo our derivative. Let's talk about what linear first order differential equations are, because otherwise this seems crazy. A first order, or Kylo Ren loving, oh no wait, they hated him, never mind, differential equation, joke number one, maybe not relatable, can be written with dy dx by itself I don't like how I wrote that. I'm going to rewrite that. Eraser. Not by itself, because that's a little confusing. With coefficient 1. That's better. I really want this to fit in one line. Coefficient 1. AKA by itself. Whew. A linear first order. Differential equation. Whew. Has the following form. This is the one we want. Can be written as, and this is the important part, dy dx by itself, bam, plus some function of x times y equal to some other function of x. So notice the functions of x cannot be functions of y, and y has to be singular also. I can't do this with y squared. That's actually something totally different and not solve this, and not solved in the same way. And then we are going to be multiplying this by an integrating factor. So I keep using that word. I need to tell you what it is. The integrating factor which is what I had up above. Remember my x cubed that seemed to come out of thin air? It's the thing that if you take, we usually call it I, and do e to the integral of whatever that p function is, dx, and multiply by. So notice there's no c here. Careful. No c. This is very strange, but it works every time. This is the weirdest method I teach, to be honest. Let's do some stuff. So what are the steps behind this? Well, the stuff I just did is the steps behind it. So let's formalize it. So the first thing you want to do is you want to make sure you put it into linear form. So solve for dy dx, put in the following form. It should be dy dx plus any stuff times a y equals to any other stuff that doesn't have y's on it. Form. First step. Next up, you need to find the integrating factor. Find I equals, I really want to write I of x, but I think I'm going to be lazy and just write I. E to the integral of that p function, it's supposed to be a p, dx, no c. No tip in your waitress on this one, because you integrate a second time later, and that's when you can introduce your c. Okay. Multiply number 1, that equation, by I. Replace the left-hand side, oops, with big D of the product of I and y, because that's what it always is. And then integrate both sides with respect to x. So this is like integrate stuff dx. So it's not dy dx like the separation of variables is. And then solve for y, if possible. It's not always going to be possible. So the first step to this is always rewrite. Find your I, multiply, create your dx, integrate, solve. Seems like a lot, but it works every time, which is the nice part about it. And I have nothing else to say other than that because it like always works. Do I really want to do 5 problems where I'm doing the same thing over and over and over and over and over again? Not really, but let's do this. Hopefully by like the second or third problem you'll have the steps down a little bit better, but here we go. All right, first step, got to rewrite it in linear first order form. This one is almost there. Remember, it needs to be dy dx plus a function times y equals to a function times x. So I need to move the y stuff over here. So, oops, dy dx plus y is e to the x. So you might be asking yourself, oh, what's my p function here? Well, p of x is the stuff times y in this linear form. And that's just a 1. It's the stuff right here is a 1. Why do I have these extra like hand doodly-doos happening down here? So that means when I go to do my integrating factor, my I of x, it is going to be e to the integral of 1 dx. Integral of 1 dx is just x, so we get e to the x. So my integrating factor, the thing I'm going to multiply by, is just going to be e to the x. Good times. All right, let's multiply everybody up. Orangey. So times everything by e to the x. So when you do that, you should get e to the x dy dx plus e to the x times y equals, well, I have something times itself, so that's e to the x squared. But when you multiply e to the x times e to the x, they have the same base. It's the same as adding their exponents, so that's e to the 2x. That's not looking like a 2. Let's try again. Woohoo! Okay, so I multiplied by my I. My next step is to rewrite this as the differential product, or my big D. EXY equal to e to the 2x. Let's step up to some integration. Integrate with respect to dx, integrate with respect to dx. Here I'm just going to get e to the xy. Over here I'm going to have to be very careful. I'm going to get e to the 2x and then over 2. Yeah, over 2. I had to think about that for a second. Plus my c. Cool. And then I'm just going to divide by e to the x, so to get y by itself. That one's kind of boring. So over here I'm going to get y equals, I'll do this division, I'll just get e to the x over 2, and this one you'll get plus c over e to the x. Or if you like, you could rewrite this as 1/2 e to the x plus c e to the negative x. That looks a little nicer. Kind of like that better. Same diff. Good times. So this is my solution. Done. Does it look like what you expected? I hope so. Let's do another one. Now this one is already in the proper form. So you might note to yourself, there's my function p, which means to find my I, I'm going to do e to the integral of 2x dx. So add 1 to the power and divide by it, you're just going to get an x squared. Alrighty, so that's my integrating factor. I'm going to take everybody in here and multiply by e to the x squared. So here I'm going to get e to the x squared dy dx plus 2x e to the x squared y equals 2x e to the x squared. Hopefully you notice and you're seeing the product rule in here. There's y and y's derivative. There's e to the x squared and e to the x squared's derivative. So there's my product rule. This is really the derivative of the product of e to the x squared and y. Let's go ahead and integrate both sides with respect to x. Ooh, I like this killer. Ooh, this side's going to be fun. This one's always easy. If you do this right, the left-hand integral is just like, boom, I get my stuff because I'm integrating a derivative. This one, not so much. So here I'm going to need to use some substitution. So I'm going to use x squared dw, the differential of w, is the derivative of w's function. Oops, 2x. Not 2x squared, I forgot to subtract. And then times the differential of x. Oh, okay. So on this side, I get the integral of e to the w dw, which when I integrate will give me e to the w plus c. Then you replace with what it's equal to, e to the x squared plus c. And once again, I'm going to have to divide both sides by e to the x. So solving for w on this side, I'm going to get e to the x squared divided by e to the x squared, which is just going to be a 1. Why am I writing that? Plus c over e to the x squared, which I think I'd rather rewrite that as 1 plus c e to the negative x squared. I like that better. Well, that's kind of cute. That's almost the witch's hat, which is the one that looks like a fun, like peaky graph that almost looks like the normal distribution. Except for, no, with that c in there, it won't be quite it. And the plus 1. Okay, well, that was something. Was something. Let's do a harder one. Do 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 do. All right. So this one is clearly not in linear form. Let's go ahead and see if we can put it in there. So the first thing I'm going to have to do is divide by x because I need to get dy dx by itself. Oh boy. So that's going to be dy dx equals y over x natural log of x. Oh no, not equals, plus. Ugh. Equals 9x squared. That came out nicer than I thought it would. Let's do our I stuff. So looking at this, my p of x function is actually 1 over x natural log of x, which does integrate, but it's going to require us to do a little bit of work to do it. So I is going to be e to the integral of 1 over x natural log of x dx. And we're going to have to do some u substitution on this. W I'm going to pick to be natural log of x. Then dw is 1 over x dx. So when you integrate this, it's going to be e 1 over w dw, which will give you e natural log of w, which will be e natural log of the natural log of x. Oh boy, did I not see that coming. I was really hoping this came out nicer than it did. Oh, but wait, e to the natural log. Those two undo each other, so this you're just going to get natural log of x. That's kind of trippy. I like it. I almost was like, this is going to be bad. Okay, so going back to our original function linear form up here, I'm going to have to take this. Actually, let me do a different color. So I'm going to take this guy and multiply by it. And then we're going to set up our d. So here you're going to get the natural log of x times dy dx and plus the natural log of x times y over x natural log of x. Oh, that's going to cancel nicely because these two will be gone. You'll just have x times y, or y over x, sorry. That's kind of nice. This one I'm worried about though. 9x cubed natural log of x. Might go well. Oh, that one's going to be nice when we integrate it, but we'll have to integrate it by parts. Let me erase this. Cool. So this jazz is our big D. Natural log of x times y equals 9x cubed natural log of x. And then let's integrate. Purple. With respect to x. I'm liking this. So this side, always easy. Natural log of x times y equals, let's do some by parts because we haven't done that in a while. U to v, v to u. I don't know about you, but I'm excited. So, oh boy. So our u, I want to pick something that I can easily derive, so that's got to be natural log of x. So then du is 1 over x dx. And then dv is going to be 9x cubed. And then v will integrate. Or is it 9x cubed? I thought it was 9x squared. It's 9x squared. I made an error earlier. That should be a 2. But here is where it's going to become a 3. Because then you'll add 1 to the power and divide by it, so you'll get a 3x cubed. Okay, that came out nicer than I thought it was going to. So let's do our by parts bit. So you get u times v, so 3x cubed natural log of x minus the integral of v du. So v, 3x squared, du. I'll divide by x, so you'll end up with 3x squared dx. I don't want to lose this first part, equals natural log of x cubed, natural log of x, minus, add 1 to the power and divide by it, x cubed, plus c. Then we'll divide everything by natural log of x and get y by itself. So here I'll get 3x cubed minus x cubed over the natural log of x plus c over the natural log of x. Oh, I like that one. It used like all of the things we know how to do. It's a good combo question. It combined everything we've known up until this point into one singular solving. Look at all those colors too. It's disaster. Let's move on to the next ones. I hope that one went okay. If you followed that one all right, you're doing good, because that was kind of hard. Okay, initial value problem. So in this case, I have a value for y, so I won't have any c's when I'm done, because I'll be able to figure out the value of c. You ready? Let's do this. Come on, there we go. So first up, dy dx by itself. I'm going to divide everybody by x cubed. Come on, pen. Ugh, dy dx equals, and I'm going to have to move the y over. Oh wait, the y is already over on the other side. Yes. Plus 2 over x cubed y. I'm writing it like that because it's easier to see what the p function is then. Because it's always just whatever you got times y. Equals 1 over x cubed e to the 1 over x squared. Oh, I see how this is going. Look, there's a function and its derivative, so that's where that's going to be. That's going to be a u substitution coming up. But we're going to get to that later. I need to figure out what I'm multiplying by first. So let's figure out our integrating factor. So our p function it's 2 over x cubed, but I'm going to write it as 2x to the negative 3 so that I can integrate it easier when I'm coming up with what my integrating factor is. So I e to the integral of 2, I'll just pull the 2 out, x to the negative 3 dx. So we'll get e2, add 1 to the power and divide by it because I'm integrating. So I'll get x to the negative 4 all over negative 4. Ew. So that's going to be e to the, negative 1/2 x to the 4th. Negative 4th. I am feeling unconfident with that value. Add 1 to the, oh, I minus 1, of course. Of course. I had a feeling this was wrong. Sorry. Add 1 to negative 3 and you get negative 2 and divide by negative 2. That makes more sense. Because then you'll end up with just negative 1 over x squared. That seems way more natural than like anything else. Because I was like looking at that and thinking, where am I going to get this x cubed from? Because it's negative x squared. Okay, cool. So let's take this and we're going to multiply everything in here by it. Hope you're ready for that. That chuckle is me being uncomfortable because I'm worried this is going to get messy. It will. All right. 2x cubed e negative 2 y. Here's where things are going to get interesting. 1 over y cubed e to the 1 over x squared e to the negative 1 over x squared. Now, hopefully you remember, when things have the same base, that means I add their exponents. You add these two, which they're going to add to 1. So here you're going to get e to the 1. No joke. Over here we have the big D, e to the negative x squared times y. Oop, don't forget it's with respect to x. So over here I'm going to have 1 over x cubed times, as we've already established, just an e to the first power. So I'm going to just leave it as e. Let's integrate both sides with respect to x. This cleaned up nicely, didn't it? I was really thinking this was going to be a horror show back up over here when I was doing p and I. Whew. E to the negative 1 over x squared y. Okay, so here, remember e is a constant, so I can just factor that out of the integral. So we can think of this as e to the negative 3. Let's see if I can not screw that up this time. Add 1 to the power, and then divide by it. Plus c. That wasn't as bad as I thought it was going to be. Okay, except for when I multiply by y, or multiply by this. Oh, that's bad. Oh no, wait, I got to divide by it. It's a negative exponent anyway, so it's the same as multiplying by the positive exponent. So here. Oh no, wait. I screwed up earlier. When you add these two, you get 0. So this is a 1. You don't end up with an E here. That was bad. Oops. Sorry about that. Okay, so. Oh, I judge myself. Take this positive 1 over x squared, because then add these two together, you get 0. E to the 0 is 1. Bam. So here you get y. Let's rewrite this. Negative 1 over 2x squared e to the 1 over x squared plus c e to the 1 over x squared. Okay, and now I got to put in 1 e and solve this to figure out what c is. Oh god. Okay, well, let's find c. So that initial value was that y of 1 is equal to e, which means y is e when x is 1. So e equals, I'm replacing y with what it's equal to, 1 over 2 times 1 squared, e to the 1 over 1 squared, looks like 12, 1 squared, plus c e to the 1 over 1 squared. So let's clean this up a little bit. E is equal to negative 1/2 e plus c times e. Oh, it looks like I'm writing letters. Okay, so if I add a 1/2 e over, I have 3.5 e's. And then c times e, if I divide by e, oh, that's nice. I get that c is 3/2. That came out way nicer than I thought. So then you just put the 3/2 in here and you're done. I'm out of space, otherwise I'd write that. That came out way cuter than I thought it was going to. I thought I was going to have fraction everywhere and nastiness. That's kind of pretty. I kind of like that one. It's cute. Let's do one more. I have a bad feeling about this one because that one went nicer than I thought it was going to. Oh no. Okay. Scrolly, scrolly, scrolly. All right. So I have good news. This one is already in proper linear form. I'm going to write it a little bit differently so you can more easily see where the p function is. I should have put this one first. I think this one's easier than that one. 1 over x y equals 0. So my q function 0, my p function is 1 over x. So that means when I do my I that I'm going to multiply by, I'm going to get e to the integral of 1 over x dx. 1 over x's integral is the natural log of x, and hopefully you remember when I combine an e and a natural log, they are inverse functions of each other and undo each other, you just get x. So I'm going to take this and I'm going to multiply the entire linear function by x. So on this side, I'm going to get x dy dx plus, and here's where this is going to get weird, x times 1 over x will just give me a 1. Y equals 0 times x will still be 0. I have a bad feeling about this one. I don't know why. These two will make a d. Big D with respect to x. xy equal to, well, 0. Now I got to integrate. Here's the thing. The integral of 0 is 0 times x plus c, so you're just going to get a c on this side. Because, when you do the derivative of c, you get nothing. The derivative constant is nothing. That's weird. xy. Oh no, don't look at that. Energy elixir. I was playing some games and stuffs. Oh, and then we just divide by x. This does not look as cute as I thought it would. Y is c over x. Huh. Okay. And then y of 2 is 2, so that means when x is 2, y is 2. So 2 equals c over 2 times both sides by 2. You get that c is 4. Huh. Y equals... I wonder if this one's separable. 4 over x. We'll just do a little cheerful aside for a second here, because I think this one I can separate. dy dx plus y over x equals 0. If I subtract this over, I'll get dy dx equals negative y over x. You totally can. This is 1 over y. dy equals negative 1 over x dx. And then you'd, ooh, we did one just like this last time. And then you integrate both sides, and then this is natural log of y. And this is negative natural log of x plus c. And then we did some e. We didn't literally do some e though. Y. Oh boy. A. Then you'll have to do a negative this 1 over x. Oh, these are the same. Oh, that's fun. Cute. I had to hop the negative up here to get negative power, so I could have that negative not in the way when you do the exponential. Anyway, don't worry about it. It's the same function. That's kind of cute. Okay, so this one was separable to begin with. See, this one you could have done either way. That's kind of fun. I like it. That's nice. Anyway, so hopefully you like integrating factors and then you like this method because it will solve things that are not separable. We've also seen ones where you solve things using separation of variables, and this one in particular you could have done either way, and actually the separation of variables was, I think, a little easier. So if you're tempted and unsure what to try first, we teach you them in the order that you should try them. Try separation of variables first. If it does not work, that's when you should try using integrating factors, or the method we did today. All right, that's all I have for you. I will see you next time, where we will do more differential equations. But the next section is a little more interesting because we're going to, use them to do some more interesting problems. In particular, we're going to get into doing some, where's my brain at? We're going to do some Euler's method, which is a solution method I think you guys will like. It's an estimating tool. That's kind of awesome. But you need to understand differentials to do it, so we had to do first orders first because they're all first orders. Cool. All right, I'll see you guys next time. Well, not literally, but you get the idea.